Good morning. Let me know if I'm audible. Thank you. Let us start the subject then. Sure. Let us start the subject now. Last class, we have started the concept of Bernoulli equation. So, mention the date first. Today is 5th of October. Last class, we were discussing the concept of Bernoulli equation. I'm going to start with the concept again, which I started last time, that is various forms of Bernoulli equation. Various forms of Bernoulli equation. From here onwards, whenever I write B dot E dot, please understand it is Bernoulli equation only. Various forms of Bernoulli equation. Now, in various forms of Bernoulli equation topic, you have to first of all understand that Bernoulli equation is an energy equation. Okay. And in fluid mechanics, there are three types of energy involved. There are three types of energy involved. One energy is pressure energy. So when I write P over here, please understand it is pressure energy. The second energy is kinetic energy. The third energy is potential energy. Okay, potential energy, remember, is always represented by capital U. That is a representation of potential energy. So basically, Bernoulli equation is saying under ideal conditions, the sum of these three energies is supposed to remain constant. What are the conditions? We'll again see later on. Okay, in the next topic, we'll be seeing those conditions. But right now, just understand that there are three types of energies, and these three energies sum is supposed to remain constant for us. Okay, so basically, one energy can convert into other energy, but ultimately the net amount of energy is supposed to remain constant. This is our idea, basic idea. Furthermore, regarding this pressure energy, please understand pressure over here does not mean force upon area. It of course means force upon area, but don't directly look at that concept. Whenever you're comparing pressure between two sections, you can say lesser area section has more pressure. You can say, imagine once again, you are having two sections, for example. You are having two sections, section 1 and section 2. Flow is in this particular direction. Flow is in this particular direction. Now you might feel that pressure at section 1 is supposed to be high. Why do you feel so? Because you see that area at section 1 is less. Therefore, pressure is high. Basically, what you are applying over here is pressure is inversely proportional to area. This is what you are applying. But all this over here is wrong. Why is it wrong? You see, if you want to apply pressure is inversely proportional to area, that is only true as long as force over here is supposed to remain constant. The force at section 1 and section 2, both of them are constant. Only then you can apply all these things. But the problem with our subject right now is force is not constant. If force is not constant, you can't directly say pressure is inversely proportional to area. That means even this concept over here is wrong. This concept over here is wrong. Okay, before writing all the forms, let me first of all discuss some basics. So first thing, please understand your misconception that lesser area is supposed to have more pressure in these kind of flows is completely wrong. Then what is pressure? Pressure over here is a pushing effect by one section on the other section. How one section or by what magnitude one section is pushing the other section. Please understand, in these cases, always start with continuity equation. Always start with continuity equation. According to continuity equation, A1 is less. A1 is less. Now, continuity equation says if A1 is less, automatically the velocity V1 is supposed to be high. The value of V1 is supposed to be high. Is it not? If V1 is supposed to be high, if V1 is supposed to be high, that means already the section in front over here is moving with a very, very high velocity. The velocity over here is extremely high. If velocity is already very high, there is not much pressure required for flow to take place. Imagine the person in front of you is moving with a high velocity in a particular line. Are you going to still push him with a high pressure? No. Since V1 is high over here, please understand, since V1 is high over here, the value of kinetic energy is high. Forget about potential for some time. The value of kinetic over here is high. If kinetic over here is high, who should be less? Pressure should be less. This implies over here the value of P1 is supposed to be less. The value of P1 is supposed to be less. This is the basic idea. This is the basic idea of pressure over here. The idea of pressure over here. Always start with continuity equation. Establish the concept of velocity. After having established the concept of velocity, then look for what pressure is. Pressure over here is like pushing effect. It is like pushing effect. Okay, whenever the velocity is high, the pushing effect required for flow to take place is going to be less. This is the basic concept we are having. Hold on to this concept. It will be easy for you to understand the various forms there. One moment, please. I'm starting now with the first form. I have discussed the first form in the previous class also. Again, I'm mentioning this over here. The first form is energy per unit. Energy per unit mass form. Energy per unit mass form. How force is not equal, this thing you'll understand in the next chapter of momentum equation. Now we can't discuss about force. Energy per unit mass over here is going to have the units. It is going to have the units of Newton meter is energy, per mass is kg, or you can say it is equal to joule per kg. Newton meter per kg or joule per kg. This is energy per unit mass. What is the format of writing this thing? The format of writing energy per unit mass is P1 by rho plus V1 square by 2 plus G times, or let us say instead of 1, let me write like this. P by rho plus V square by 2 plus G times Z is supposed to remain constant. This is energy per unit mass. Every term over here is going to have SI units of joule per kg. That is a concept. Now coming to the second form. The first form, remember, is not important. This form is not important. This is a not important form. The second form is slightly important form. This is known as energy per unit volume. Energy per unit volume. Energy per unit volume form. Now this energy per unit volume form is going to have what SI units? What is the SI unit of every term over here? Energy is Newton meter. Per volume means by meter cube. That is equal to how much? Newton per meter square. That is equal to Pascal. Every unit over here, or every term over here is going to have the units of Pascal. That means every term is supposed to represent some type of pressure. The form over here goes something like this. P plus rho V square by 2 plus rho G Z is supposed to remain constant. This is the format we are going to have. P plus rho V square by 2 plus rho G Z equal to constant. Now, each term is having a special name. Let us start writing the names over here. The term P over here stands for static pressure. It stands for static pressure. Half rho v square or rho v square by 2. Very, very important pressure. Half rho v square or rho v square by 2, it is called as dynamic pressure. It is called as dynamic pressure. Then you have rho gz. This rho gz over here is known as hydrostatic pressure. It is known as hydrostatic pressure. Hydrostatic pressure. Okay, these three pressures are there. Apart from these three pressures, you are going to have a combination set also. The first combination set you are having is first two added up. That is P plus rho v square by 2. It is called as stagnation pressure. Stagnation pressure. It is called as stagnation pressure. Next, you are having rho gz. P plus rho gz. P plus rho gz. This is called as piezometric pressure. You will understand why these names are there. Piezometric pressure. This stagnation pressure, from here onwards, I'm going to represent as PSTAG, and piezometric pressure by P with a star on top. This is how I'm going to represent. So this is basically two forms. Now I'm going to discuss the definitions of each of these pressures. First of all, static pressure, very simple. You are standing in a queue. You are pushing the person in front of you. The pressure you are pushing him with is known as static pressure. Okay. Static pressure basically is pushing effect. Very simple. Pushing effect by one section on other section. Okay. Now, what is dynamic pressure? Imagine when you are moving, the person in front of you suddenly gets blocked. Someone is blocking him. The moment someone blocks him, please understand, the moment someone blocks him, his kinetic energy is going to decrease. If his kinetic energy decreases, some other energy is supposed to rise up. You see, you're only having two options now. Either potential, gravitational potential is rising up, or pressure energy is rising up. If you say gravitational potential energy is rising up, you basically mean that the person is now, after getting stopped, the person is now moving vertically up. That is not happening. Instead, what is happening? Instead, the pressure energy over here is rising up. So whenever kinetic energy is decreased, there has to be an equivalent rise in pressure. That equivalent rise in pressure over here is your half rho v square. It is known as your dynamic pressure. Now, generally people have a doubt over here that when I'm making the velocity zero, if I make the velocity zero, then kinetic energy is decreasing. Accept it. If I write over here that velocity is zero, even dynamic pressure will become zero. That is wrong. Okay. When you are making velocity zero and then you're checking dynamic pressure, over here in place of V, you are supposed to write the initial velocity which was there before becoming zero. Imagine I was having a velocity of 3 meters per second. Example, say, someone blocked me. My velocity over here became zero. This, let us say, is V1. This, let us say, is V2. For finding out the value of dynamic pressure, which velocity should I put? I should be putting V1, not V2. If you keep putting V2 every time, dynamic pressure becomes zero. There is no point of defining dynamic pressure. So I hope you are following this thing. The velocity before becoming zero is supposed to be put over here. That is a basic idea. After this thing, imagine you are having some elevation. You are initially having some elevation. Suppose you are having some data. Imagine a pipe, something like this. This end is having some elevation initially. Okay, some extra Z it was having. I make the pipe like this. When I make the pipe like this, then what is happening? Once again, if I am decreasing the elevation, then what is happening? Then the potential energy is coming down. If the potential energy comes down, who should rise up over here? The pressure energy should rise up over here. That rise in pressure, because potential energy is coming down, is known as hydrostatic pressure. It is known as hydrostatic pressure. Again, please look over here. Imagine the pipe was like this. Okay, there was a pipe like this. Let us say I'm hinging the pipe over here. After hinging the pipe over here, I brought the pipe at this particular level. So what is happening now? Its datum is keeping on decreasing. If its datum keeps on decreasing, then the value of U is decreasing. Then who is increasing over here? Pressure energy is over here increasing. That rise in pressure energy is known as your hydrostatic pressure. Again, when I'm taking this Z over here to define hydrostatic pressure, which Z should I write? Imagine this Z is Z1 and this Z is Z2 over here. Z1 is equal to 4 meters, Z2 is equal to 0. Which Z will I write? Again, I will write the initial Z, which was there, which later on became 0. So that means I'm supposed to write Z1 over here. I hope you are following all these things. Very good. Okay. This is regard. See, this entire equation over here is just you are removing some money from one pocket, putting into other pocket. That is it. You are having three pockets over here. Money is basically energy. Ultimately, with you, the net amount of money is still remaining constant. You are just putting from one pocket to other pocket. That's it. Okay. So if I say that from, let us say, my trousers pocket, I'm putting into my shirts pocket. Okay. So that is something like trousers pocket energy is decreasing, shirts pocket energy is increasing. That's something like that. Okay. Try to visualize things now. Actually. Now I'm going to write everything in statement so that it will be helpful for you later on, because I know many of you will forget things. Okay. Sometimes I am afraid that I might forget things. With practice only, someone has asked a very, very good question. Okay, I'll mention that question also. One second, wait on. Okay. There are some questions. I'll address all these questions when time comes in. Okay. Don't worry. One question that has arrived over here is when the value of U is coming down, when the value of U is coming down, why are you just saying that the value of P is increasing? Why don't you say the value of kinetic energy is increasing? That is a good question. The answer to that question is why kinetic energy is not increasing is the reason is if kinetic energy is increasing, the question should say the discharge is changing. If this pipe I'm changing into this pipe condition, okay, and nothing else is mentioned, I would assume the discharge initially and later on both of them are same. Remember this thing. Something regarding discharge should be mentioned for me to talk about K. Okay. Otherwise, we are always going to assume only pressure is increasing. Remember this thing. Pressure takes the headache of changes every time. Okay. Someone has asked me regarding whenever you create a barrier, then that barrier is going to experience some force. That thing we will see in the next chapter. What will happen over there, that thing will be seen in the next chapter. And someone had asked me regarding why not take Z1 minus Z2. That is exactly correct in in that particular diagram. What you said was exactly correct, but the value of Z2 I had taken as 0. Therefore, I'll just write. Anyway, all these things you'll understand as we keep on doing the problems. Now wait on for some time. Don't mention anything. Okay. Don't mention anything. Let us now mention the names of all these pressures. The first pressure, if you remember, was named as static pressure. It was named as static pressure. The static pressure is represented by capital P. Static pressure is represented by capital P. How do we define this thing? The pressure exerted by one section of a fluid on its adjacent section. Now, why is it exerting this thing? In order for flow to take place. The pressure exerted by one section of fluid on its adjacent section in order for flow to take place, that is known as your static pressure. Keep it. This is the first thing. The second pressure over here is known as dynamic pressure. Dynamic pressure. This dynamic pressure is rho v square by 2. Dynamic pressure is rho v square by 2. Now, how do we define this dynamic pressure? The rise in pressure, the rise in pressure due to drop in kinetic energy. Due to drop in kinetic energy. Now, I can immediately write over here. There is no need of mentioning actually the sum of static and dynamic pressure is known as what? Stagnation pressure. But still I'll mention the point at which kinetic energy becomes zero is stagnation point. It experiences both. It experiences both static and dynamic pressure. Static and dynamic pressure. It experiences both static and dynamic pressure. Therefore, what should happen? Therefore, P stagnation has to be equal to how much? P plus rho v square by 2. It has to be P plus rho v square. This is a second type of pressure along with stagnation pressure discussed over here. The third type of pressure we are having is known as hydrostatic pressure. Hydrostatic pressure. This hydrostatic pressure is represented by rho g z. It is represented by rho g z. The rise in pressure, due to drop in gravitational potential energy. Gravitational potential energy. The rise in pressure on account of drop in gravitational potential energy is known as hydrostatic pressure. The sum of static and hydrostatic pressure, is going to be equal to what? Piezometric pressure. Okay. Sum of P static and P hydrostatic is P piezometric pressure, which basically implies this piezometric pressure is represented by P with a star over here. The value of P star is equal to P plus rho g. This is regarding the various pressures we are having. Okay. This is regarding the various pressures we are having. Let us now move further. The next thing. Moving further, the next, you can take a snapshot of this particular slide if you want. Be quick. After having understood these pressures, the next case we are taking over here, is a third form. The third form is energy per unit weight form. Okay. The third form of discussing Bernoulli equation is energy per unit weight form. Energy per unit weight form. This energy per unit weight form is supposed to have the units, SI units as, see, energy is Newton meter divided by Newton, that is going to be equal to meter only. So basically every term over here will be representing something called as head of energy. Okay, head of energy is basically energy divided by weight of that particular fluid. Now what is the format you're going to have? The format over here is P by gamma plus V square by 2G plus Z is equal to constant called as capital H. Over here, P by gamma is known as static or pressure head, static head or pressure head, pressure head. V square by 2G over here is known as, there are multiple names for this thing. Some call it as dynamic head, some call it as velocity head, some call it as even kinetic head. Kinetic head. Okay. Z over here is known as datum head. Z is known as datum head. So these are the various names. These are the names of various heads we are having over here. If someone wants first slide, you can take the first slide. You can take a snapshot for the first slide. Sorry. Now let me explain you the physical meaning of each of these heads, how to visualize each of these heads. To understand how to visualize each of these heads, you have to know some basics, that whenever you want to measure the velocity at a particular point in a flow, you are going to use two devices. One device is known as pitot tube. Along with pitot tube, we require piezometer. Okay, let us see the diagram now. To understand this better, let us see a diagram. Imagine you are having some pipe flow taking place. There is some flow taking place in a pipe. Imagine there is some flow over here. Let me first of all draw a diagram. Imagine there is some flow taking one second. There is some flow taking place in this particular pipe, let us see. In this pipe, there is some flow taking place. Now, what I want to do is, at a particular point, let us say some random point over here, at this particular point, suppose some point A, I want to find out how much is the velocity. This velocity is called as local velocity. Remember, there are two types of velocities. One is local velocity, the other is average velocity. Local velocity will keep on varying from here to here. Along a particular section, everywhere you'll be having different local velocity. At the boundary zero, center maximum. Some random point I'm taking, I want to find out the local velocity. The logic over here is to find out local velocity. You first of all stop the flow. At that particular point, you stop the flow, convert that velocity into something else and measure that thing. So for example, over here, I'm going to install a particular device. That device would be something like this. The device, let us say, is a tube, something like this. This tube is known as a pitot tube. This tube is known as a pitot tube. And this particular, that initial point of pitot tube is called as nose of pitot tube. It is called as nose of pitot tube. Now, what happens when you install a pitot tube? Please try and understand what exactly is happening the moment you install a pitot tube. Excuse me. The moment you install a pitot tube, the first thing that will happen is at point A, the fluid stops. The fluid is going to experience stagnation at point A. How is it so? Imagine, please imagine, look at my cursor now. Keep looking at my cursor. The jet of fluid is coming and it is striking over here, stopping. So this point where my cursor is right now, that becomes a stagnation point. Then the next jet of fluid comes and stagnates somewhere over here. Likewise stagnates over here. Likewise stagnates over here. Likewise stagnates over here. Ultimately, at point A, you are going to have a steady stagnation point. The fluid will stagnate over here. The moment point A experiences stagnation, what happens is the fluid now is going to experience at point A pressure equivalent to stagnation pressure. So point A is going to have stagnation pressure. It is going to have stagnation pressure. If it is having stagnation pressure, now go back to fluid statics. If it is having stagnation pressure and you are exposing it to atmosphere, then that pressure is going to get converted into some head. It is going to get converted into some head. So basically, the fluid will rise up to some level. The fluid over here rises up to some level so as to maintain that pressure. Let us say the fluid over here is rising from here up till here in order to maintain this much of pressure. Now the question is, what is this particular height called as? Recall a statement I have given you in statics. The height of a fluid column required to measure a particular amount of pressure or required to create a particular amount of pressure is known as, one second, my cursor is not working over here. 1 minute, please. Yes, recall, I told you in fluid statics, the height of a fluid column required to create a certain amount of pressure is called as what? What is that height called as? Very good. It is called as head. It is called as head. Since it is called as head, now look over here. Since this is called as head, and it is called as head for which pressure? This is called as head for which pressure? This over here is called as head for stagnation pressure. Therefore, this has to be equal to H stagnation. This has to be equal to H stagnation. How much is H stagnation equal to? H stagnation will be equal to P stagnation divided by gamma. Remember, I told you, excuse me, I told you that whenever you want to calculate head, all you have to do is take the pressure divided by gamma. So P stagnation by gamma. Recall what was P stagnation? P stagnation was P plus rho V square by 2. If I divide this entire thing by gamma, I'm going to get over here P by gamma plus V square by 2G. P by gamma plus V square by 2G. So this particular device over here is helping me identify the value of stagnation. But I want velocity. If I want velocity, then I have to remove this P by gamma somehow. If I remove P by gamma, I will be left only with velocity. From there, I can calculate the velocity. For that purpose, I am going to use the next device now. This device is known as piezometer. Now, what will piezometer do? Let us say just above point A, somewhere over here, I am creating a particular device, let us say. I'm creating a particular device, and this device is not blocking the flow, but it is exposing the flow to atmosphere. If this device is exposing the flow to atmosphere, then what happens? Then what happens? The fluid is going to rise up till some level. The fluid is going to rise up till some level over here. Now, you might have a question, why is the fluid rising up till this particular level? The reason for fluid to rise up till this particular level is it has to maintain the static pressure at this particular point. Recall, this point is already having some static pressure initially. To maintain that static pressure, the fluid has to have some head over here. So basically this head over here, is representing your static head. This head over here is representing static head. So this is static head. H static, and the value of H static is equal to how much? P by gamma. H static is equal to P by gamma. So if this is H static, if this is H stagnation, then what happens? The difference over here is supposed to be equal to how much? This difference over here is supposed to be equal to H dynamic. This is supposed to be equal to H dynamic. So basically, when I use a pitot tube, this is a pitot tube, and this over here is a piezometer, the difference in the reading is going to be equal to H dynamic. It is going to be equal to H dynamic. From here I can say that V square by 2G has to be equal to H dynamic. H dynamic. Instead, let me do one thing. Instead of writing H dynamic, let me just write H over here. Let me just write H over here. So it is going to be equal to H. This implies the value of velocity has to be equal to root over of 2G H. Now, which velocity is this? This velocity over here is known as theoretical velocity. This velocity over here is known as theoretical velocity. There can be some errors over here. That's why it is called as theoretical velocity. The value of actual velocity will be equal to CV into root over of 2G H. CV into root over of 2G H. CV over here is called as coefficient of velocity. Coefficient of velocity. CV is known as coefficient of velocity over here. Okay. So this is the concept basically of a pitot tube along with a piezometer. I hope you are able to understand all these heads over here. Okay. One more thing I want you to understand is, imagine that I have chosen a particular reference level somewhere over here. I have chosen a particular reference level. This is a reference level I have chosen over here. This reference level I'm calling as my reference datum. At this particular level, the value of Z is equal to 0. It's a horizontal level. Now, this Z is equal to 0 level is up to you. You can choose wherever you want. You can choose wherever you want. Okay. So now, after having chosen this reference level, let us say I draw over here this height. Now, what is this height over here representing? What is this height over here representing? This height over here is representing your datum head Z. So this is datum head. Along with this, you are having stagnation head. So this complete height from here till bottom, this complete height is going to be the total head capital H. Similarly, let us say I draw over here this height. I draw over here this height. This is again datum head. We know that this again is representing what? Datum head. This again is datum head. So what is this complete height over here going to represent? You see, it is representing static head plus datum head. This height over here is known as piezometric head. This height over here is known as piezometric head. That means from this bottom up till here, it is known as piezometric head. Okay. This is regarding the concept of energy per unit weight along with the concept of pitot tube with piezometer in order to measure the local velocity in a particular flow. I hope this is all clear to you. You can take a snapshot of this thing. At A, the velocity was non-zero. Later on, it became equal to 0. So basically, you're converting, you're converting the velocity at point A into some head over here. First of all, what you did, you converted velocity at point A into pressure. That pressure you converted into head. So there was some velocity. That velocity has now taken over here as head. Now someone is asking me, why is the water rising in a piezometer? What is the reason? What is the reason? Wait on. What is the reason for water rise in a piezometer? The reason for water rise in a piezometer, please understand that already when there is a particular pipe, there is going to be some pressure inside that. There is going to be some pressure inside that particular pipe. Okay. That pressure over here is what pressure? Static pressure. It is static pressure. The moment you expose it to atmosphere, in order to maintain that much amount of static pressure, the fluid should have some head, is it not? The fluid should have some head. Imagine the side view of this particular diagram. Imagine the side view of this particular diagram. Let me show it in the side view. The side view of this diagram would be something like this. That you are having a pipe something like this. Let us say you are having a pipe something like this. This is a pipe, let us say you are having. Now, if I say that there is a particular point over here, there's a certain point over here, point E. I want to find out the pressure at point A. So what would you say? You would say at this particular level, please install something called as a piezometer. You would say install a piezometer. Install a piezometer, let us see. One second. Install a piezometer. If you install a piezometer, then what will happen? The fluid, which is the pressure over here, so you're having certain amount of pressure over here. In order to maintain that much amount of pressure, the fluid is supposed to rise up till some level. The fluid is supposed to rise up till some level. This head over here is equal to your H static. This is equal to your H static, which is equal to PA divided by gamma. Please try and understand this thing. Look at this image and look at this image. The side view of this will be circle. That is a circle you are having. The side view of this tube is going to be again a tube. Same tube you are having over here. Are you following? This is what you have studied in your basics of what you call pressure measurements, right? Same thing over here. Okay, someone is asking me, can you take A as reference data? Yes, you can take A as reference data in that case. Why do we use coefficient of velocity? I'll come to that point again. Let me explain this diagram again for those who did not understand. It is not that much difficult. You wait for some time. Wait for some time. Okay. First of all, what is the difference between a pitot tube and a piezometer? This over here is a pitot tube. This is a pitot tube. Remember, a pitot tube is always going to block the flow. The purpose of pitot tube is to create stagnation. Okay. It is supposed to create stagnation. But look at a piezometer. This over here is a piezometer. This is a piezometer. Look at piezometer. Piezometer is not blocking the flow anywhere. It is not creating stagnation anywhere. So first difference you can understand. A pitot tube will block the flow. A piezometer will just expose the flow to atmosphere. So basically, when it is blocking the flow, please understand this thing. It is converting velocity into pressure. It is converting velocity into pressure because when he blocks the flow, velocity becomes zero. So velocity is converting into pressure. After blocking the flow, he's doing one more thing. He's exposing it to atmosphere. So now at this particular point, you have developed stagnation pressure and you're converting stagnation pressure into head. Okay, you're converting because you're exposing it to atmosphere, you're converting stagnation pressure into head. So therefore, this is called as H stagnation. H stagnation is basically P stagnation by gamma. I can write over here. H stagnation has to be equal to P stagnation divided by gamma. It is supposed to be P stagnation divided by gamma. Fine. So that is why you are going to get the values P by gamma plus V square by 2G. From there, you can get this all value. Why CV is coming, all those things I'll discuss again. Okay, in the next topics, coming topics, later I'll be discussing why CV is coming. CV is called as coefficient of velocity. That will come. Okay, mostly the value will be 0.99, 0.98 or 1 only. Okay, don't worry about that. Now moving further, what is piezometer doing? See, piezometer is not blocking the flow but exposing it to atmosphere. When it is exposed to atmosphere, think logically, when it is exposed to atmosphere, in order to maintain the pressure at point A, the fluid should rise up to the corresponding height. That height is what height? Static head. That head over here is static head. In order to maintain that particular pressure, static head is going to develop over here. That is equal to PA by gamma. This is the concept over here. Now the difference is what? You see, very simple. Here you did not stop velocity. Here you stopped velocity. So basically difference is going to be equal to velocity head. The difference is going to be velocity head. From there I'm getting this concept. I'm getting this answer. Not that much difficult. You refer to this again after the class. This slide, you refer to this again after the class. You'll find it quite simple only. Okay. This is the concept of energy per unit weight form. Let me move further. I'm leaving this slide as it is. I'm going to the next slide now. In this particular slide, I'm going to discuss someone is asking me, can datum be inclined? No, datum cannot be inclined. You see, datum is basically a reference from which you are going to measure your gravitational potential energy head. And gravitational potential energy head is always vertically up. If it is vertically up, datum should be completely horizontal, is it not? If there is no flow taking place, then piezometer reading and pitot tube reading both will be same. Point A is just some point I'm considering. Point A is some point I'm considering in a particular flow. Now let us move further. You see, if I keep answering these things, it will take a lot of time. Let me move further now. The next thing I'm going to discuss over here is an important concept. It is called this concept over here is called as limitations and assumptions required in Bernoulli equation. So let me write over here limitations and assumptions in Bernoulli equation. What are the various limitations and assumptions in Bernoulli equations? Let us see over here. First limitation we are going to have. First point. Bernoulli equation in its original form is valid only for steady and incompressible flow. This is one limitation we are having. So whenever Bernoulli equation is applied, you have to always assume that the flow is steady and incompressible. If the flow is compressible, previous class I gave you that particular form. It was having integral dp by rho plus v square by 2g plus z. I'm sorry, v square by 2, not 2g, v square by 2 plus gz plus gz is going to be equal to constant. This was a form for compressible flow. If it is incompressible flow, then P by gamma and all those things you can write down. So this is the first limitation, very simple limitation. Coming to second point. Now this second point is only for mechanical people. For civil people, if you can remember, remember. If you cannot remember, don't worry. Nothing will happen if you forget this point. This is purely a mechanical engineering based point. The logic is, you see, mechanics said that kinetic energy plus potential energy is equal to constant. This is what mechanics said. Fluid mechanics is saying pressure energy plus kinetic energy plus potential energy is equal to constant. But in reality, when you deal with real flows taking place, you can have something called as heat transfer. So strictly speaking, the equation should be heat energy plus pressure energy plus kinetic energy plus potential energy is equal to constant. Strictly speaking, this should be the equation we are having. But we do not have this equation right now. We only have these three terms over here. That means Bernoulli equation does not deal with the heat transfer effects involved in a particular flow. I hope this point is clear. Regarding the details of this point, you don't have to worry about in my subject. The details will come in thermodynamics, where you study the concept of steady flow energy equation, that is SFEE, very, very standard equation we are having in thermodynamics. Over there, you'll come across it. Over here, I'll just write a statement. The statement goes something like this. Bernoulli equation doesn't consider the heat transfer effects. Heat transfer effects involved in a flow. Involved in a flow. This is the second point I'm having. First two points are very simple. From third, fourth, three more points I'm going to discuss. These are very, very critical points. From these 3 points, you can expect problems coming in. Okay. Third point over here. Third point. Remember one thing. Whenever you are having a flow that is rotational, then different streamlines have different total head. Let me write this thing. I'm writing in different ink over here. In rotational flow, different streamlines have different total head. In the case of rotational flow, different streamlines are going to have different total head. Now, what is the meaning of this thing? In this particular slide, we'll just refer to this concept. Okay, please don't ask questions now itself. You listen. I know what difficulty you'll be having in understanding, but you have to be patient to understand that. You listen to everything. Why this happens, all those things you'll be having some doubts. Now only you don't start typing in. Okay, you wait. Okay. Imagine you are having a set of streamlines. You are having a set of streamlines. Some 4 streamlines I have taken over here. Okay. Imagine that this is psi 1, this is psi 2, this is psi 3, this is psi 4 over here. N number of streamlines I'm having. The total head in psi 1 is capital H1. The total head in psi 2 is capital H2, capital H3, capital H4. Let us say, for the sake of understanding, let us say that between psi 1 and psi 2, the flow is rotational. So you are having rotational flow over here. Between psi 2 and psi 3, the flow is irrotational. No rotation. Again, between psi3 and psi4, you are having flow that is rotational. So this again is rotational over here, rotational over here. Now listen to this. According to the statement, in rotational flow, let us say flow over here is rotational. Different streamlines have different total head. That basically means HO1 is not equal to H2, because between these two streamlines, the flow is what? Rotational flow. They're supposed to have different total head. But what about psi2 and psi3? The flow over here is irrotational. If the flow over here is irrotational, that basically means both the streamlines are supposed to be having same total head. Both of them are having same total head. H2 and H3, both of them are same. Now tell me, can I write H3 is equal to H4 over here? No. The reason is over here again rotational. That means even though these two are equal, but they are not equal to H4 over here. This is the concept. So basically, whenever you are having, one second please. Basically, whenever you are having rotational flow, two different streamlines, different total head. Irrotational flow, in irrotational flow region, all streamlines will have same total head. Imagine between psi2 and psi3, I can have n number of streamlines taken. Just imagine, I can have n number of streamlines taken between psi2 and psi3, because streamlines are imaginary concepts. You can take streamlines anywhere. Only thing, the flow should not cross the streamline. So I can have n number of streamlines. All these streamlines are supposed to have same total head. All the streamlines are supposed to have same total head. And over here, between psi1 and psi2, I can have n number of streamlines. All of them will be having different total heads over here. This is a concept. To understand this better, let us do one thing. Let us take a particular point A over here. Let us take a point B over here. Let us take a particular point C over here, a point D over here, a point E over here, a point F over here. Question number 1. Okay, don't type in, just answer it to yourself. Can I write HA equal to HB? The answer is yes. I can write HA equal to HB. Okay, I did not speak about losses till now. Forget about losses. Forget about losses. Just think logically now. Can I write HA equal to HB? The answer is yes, because I'm moving along streamline. Along streamline, I don't have a problem. Across streamline, I'm having a problem. Along streamline, every time the Bernoulli equation is valid, it is fine. But can I say this is equal to HC? The answer is no. These two are even though equal, but they are not equal to HC because you are jumping the streamline now, going across. That is not allowed in rotational flow. Can I say HC equal to HD? The answer is yes, because the flow is irrotational. Therefore, HC and HD, both of them are equal. But is HD equal to HE? The answer is no. They are not equal to HE. Why not equal to HE? Because in between the flow is rotational flow. Can I say HE equal to HF? Yes, again I can say so. Along the streamline, every time you can go. Across the streamline, only in irrotational flow you can go. This is the concept regarding the third point. Now, some of you might be having a doubt. Why are the energies at these two levels different? The reason for the energies at these two levels to be different is because, remember this thing, whenever you want rotation to take place, one layer is supposed to have higher energy, the other layer is supposed to have lower energy, only then the fluid element is going to rotate. Since higher energy and lower, imagine upper layer higher energy, lower layer lower energy. So therefore the total head also in both these layers are supposed to be different over here. So this is regarding the third point we are having, very important point. Okay. Moving further to the fourth point now. Point number 4. Point number 4. Now regarding this point, very important point again. Okay, probably the entire slide will be taken only for this particular point. What is this point dealing with? You see, in a flow, many times you'll be having problems dealing with the concept of what do you call
turbine, the concept of pump. These things will be involved in a flow. But Bernoulli equation, if you see, look at the Bernoulli equation. The Bernoulli equation you're having over here is not mentioning anything regarding turbine or pump and all these things. So now in this particular slide, we are going to overcome that limitations. So the problem right now we are having is Bernoulli equation. Bernoulli equation doesn't mention regarding the energy transfer due to pump or turbine. Okay, right now Bernoulli equation is having this limitation, but we can overcome it. It is not such a big deal. We can overcome this limitation very easily. We can overcome this limitation very easily. Imagine, first case I'm having over here is a pump. Let us talk about pump first of all. Ask yourself, what does pump do? Does pump increase the energy of the flow or decrease the energy of the flow? Remember, pump is going to increase the energy of the flow. Okay. So imagine I'm having some flow taking place. I'll draw a line diagram now. A flow taking place. And in between I'm having a pump. Then flow further takes place. Flow further takes place. Let us see the flow is taking place in this particular direction. Flow is in this particular direction. Suppose I'm taking a section over here. This section is section 1. I'm taking another section over here. This section over here is section 2. Okay. The problem right now is I cannot write over here H1, that is total head 1, and total head 2. Both of them are equal. Both of them are unequal. Okay, I hope you all got this thing, that both of them are unequal, because pump is going to give some energy to the system, to the fluid. Now, if they are unequal, the next question is, what is the sign of inequality that is supposed to appear over here? Which sign of inequality is supposed to appear over here? You see, if H1, H2, both of them are unequal, who is greater over here? Ask yourself this thing. You see, the head at 2 is greater because pump is giving some extra energy. Imagine you're traveling with 100 rupees in your pocket. Someone comes in between and gives you, let us say, some 50 rupees. So later on, how much you're going to have? 150 rupees. So basically, at the next section, you're going to have higher energy. At the next section, you're having higher energy. If at the next section you're having higher energy, then you can say H1 and H2 can be equal, provided I subtract over here something. How much should I subtract over here? I should subtract over here HP. I should be subtracting over here something called as HP. This HP over here is known as head of pump. Imagine one thing is less, one thing is more. If I want to make both of them equal, I should say the higher thing minus whatever is the deficit, whatever is the difference. Then I'm going to get this value. HP over here is known as head of pump. Now, I can write the entire equation as P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2, and I have to subtract over here HP. I have to subtract over here HP. If you are finding this difficult, just ask yourself, okay, he is lesser. If he is lesser, I have to add over here something so that he becomes equal. But the convention, remember this thing, convention is addition or subtraction should be done in Bernoulli equation on the right hand side only. So adding something over here is as good as subtracting something over here. So subtract over here, that's it. Okay, again, he is less, you have to add something, instead subtract over here. That's the concept. Okay, what is HP over here called as? HP is basically head of pump. Now what is it equal to? It is equal to energy received by fluid from pump divided by weight of the fluid divided by weight of the fluid. Remember, head means energy per weight. Therefore, energy received by the fluid from pump divided by weight of the fluid. This is the concept of pump. This is the concept of pump. One second, please. Now coming to the second case. The second case I'm right now having is a turbine, is that of a turbine. So let us take the case of turbine. Turbine is exactly the reverse process. Turbine is not going to give you energy. Turbine is actually going to Turbine is not going to give you energy. Turbine is actually going to take away energy. Turbine is actually going to take away energy. So imagine you are having a pipeline. In between, you have a turbine. In between, you have a turbine. Let us say the flow is taking place over here. Flow is taking place over here. This is section 1. This is section 2. Now I'll question, you answer it to yourself only. The question number 1 is H1 and H2. I hope you have understood till here that both of them are not equal because turbine is taking away some energy, taking away some head. Therefore, both of them are not equal. Who is going to be greater over here? As you move forward, he is someone who has taken away money from your pocket. You are having 100, he took away some 20, you are having 80 over here. So basically this head H1 over here is supposed to be greater. H1 is supposed to be greater. How to make it equal? If he is greater, you subtract something over here. But I told you, everything should be done on the right hand side. So subtraction over here is as good as addition over here. So now I can write over here, H1 is equal to H2. H1 is equal to H2 plus head of turbine. Plus head of turbine. Very simple mathematics. So now you can write the equation as P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2, not to forget over here, plus HT. What is HT over here called as? Head of turbine. HT over here is head of turbine. Now what is the meaning of head of turbine? It is energy. Previously fluid was receiving energy. Now you think logically, what is fluid going to do? It is going to give energy. Energy by the fluid, given by fluid. To whom is fluid giving energy? To turbine. Energy given by the fluid to turbine per unit weight of the fluid. Per unit weight of the fluid. This is the concept of fourth slide over here. I hope this is clear to all of you. See, you do not compare energies, you always compare head. The reason is weight of the fluid is not defined. Weight is continuously moving forward. That is why we go for per unit weight. Okay. It is only for steady flow, please. Numerator of both the heads. You see, good question, Shiva. I'll explain the numerator of both the heads again. Okay, someone wanted this slide. Quickly take down this slide. Take down the slide quickly. You have taken a snapshot, and then you can take a snapshot of this slide. I'll discuss the numerator of both these heads. That's a good question actually. And if it is possible, please write down in a rough book, in a book if you're having, write down this thing, because in the next slide, I want you to see this particular words. Energy received by the fluid from pump by weight of the fluid. Energy given by the fluid to the turbine by weight of the fluid. Write down those things. Steady incompressible need not mean ideal. Now look over here. Imagine that I'm having a pump over here. There is a flow taking place forward. Section 1, section 2. Okay. I'm having, let us say, pump is giving some 100 units of energy. But practical problem is when pump is giving 100 units of energy, complete 100 units cannot be received or achieved by the fluid. Fluid is able to receive. Fluid is receiving, let us say, something less, generally because of some losses. Okay, losses in the pump. I'm not telling fluid losses. I'm talking about the machine losses. Okay, pump will have some machine losses. Because of that, fluid will receive something less, let us say 80 units. Now the question is, Bernoulli equation, ask yourself this question. Bernoulli equation is written as an energy equation for whom? Is it for pump or the fluid? Ask yourself, is it written as an energy equation for pump or the fluid? The answer is Bernoulli equation is energy equation for the fluid. If it is an energy equation for the fluid, who is more important? What pump is given is more important, or what fluid is receiving is more important? What fluid is receiving is more important. Imagine I am giving you 100 rupees. Okay. But somehow while I'm giving you 100 rupees, some 20 rupee note fell down. Because of some problem, 20 rupee note fell down. When you talk about your energy equation, will you say that you got 100 rupees or you got 80 rupees? I gave 100, fine. But how much are you getting? That is your energy equation. So you'll talk only about 80 rupees over there. That is what. Whenever you deal with pump, energy received by the fluid from pump becomes important for you per unit weight of the fluid. Okay. Now come to turbine. In the case of turbine, imagine you're having a turbine over here, section 1, section 2. This is where the flow is taking place. Let us say fluid has given 100 units of energy. Turbine again is receiving something less. Turbine is receiving 80 units of energy. Again, ask yourself the same question. Bernoulli equation is written as an energy equation for whom? Fluid or turbine? Answer is Bernoulli equation is for fluid. So what is important over here? In this equation, 100 is important or 80 is important? I hope you're getting the answer. What fluid is giving away is important. He is receiving or not receiving, it is his headache. It is not fluid's headache. It is the turbine's headache. He has given 100 units. If turbine is not able to receive, turbine's headache only for me. Fine. So that is why whenever we write about turbine, we say energy given by the fluid. Check over here. The words are very important. I did not write energy received by the turbine from fluid. वो गलत हो जाता. That would be perfectly wrong. I'm writing energy given by the fluid. उसके बाद turbine क्या कचरा कर रहा है उसका मतलब. That is his headache. It does not concern with Bernoulli equation for us. This is the concept. See, these are very simple things. Okay. Over here, what we are doing, whenever energy difference is there, that time what should we add, what should we subtract, we are seeing over here. That much only. Okay. Chaliye. Let us move further now. Energy given means what? You will understand that once you enter into hydraulic machinery, just understand that whenever you are going to have, imagine you're having some fluid over here. You want to lift the fluid to some particular level. So what will happen? You will install over here something known as pump. What will pump do? Pump will give high pressure to the fluid. It will increase the pressure. By the virtue of increasing pressure, the fluid will reach up. So what is pump doing? Pump is giving energy over here. Now imagine fluid is coming. you're having some turbine over here. You're having some turbine over here. The moment fluid strikes on a particular turbine, then what will happen? The fluid's energy is going to convert into the motion of this particular turbine. So fluid's energy is decreasing. So fluid is basically giving energy to the turbine. Likewise. Okay. Chali, let us move further now. Final point now. I have spent a lot of time on fourth point, quite satisfied. Final point over here. Please wait for some time. Don't start writing again. Okay, what about losses? That's what. You be patient. I will tell you subject. Okay, you should trust the faculty. He will give you the subject. Now I'm talking about losses only. Someone is asking me already about losses. Don't worry. Yeah. If I give you things randomly, you will not understand. Things should come in particular sequence. The sequence is losses will come now. Now you can understand losses perfectly. Remember, when we were talking about Bernoulli equation's existence, we started with Euler's equation. In Euler's equation, we have neglected viscous forces. If we neglect viscous forces, the present form of Bernoulli equation becomes valid only for ideal flow. Okay. The present form of Bernoulli equation, the present form of Bernoulli equation. What do I mean by this? Present form of Bernoulli equation means P by gamma plus V square by 2G plus Z is equal to constant in a flow. Is valid only for which flow? For ideal flow. Okay, this form of Bernoulli equation is right now valid only for ideal flow. Okay, this is a limitation we are having. So now we have to worry about what happens to Bernoulli equation real flow, because every time we are going to deal actually with real flow only. So now the question is, what about Bernoulli equation in real or actual flow? Real or actual flow. Bernoulli equation in real or actual flow. What happens now? Please understand this thing. Whenever you are having a real process taking place, there will be some resistance against that real process. Some resistance should be there whenever real process is there. To overcome that resistance, the system will give away some energy or do some work which it does not desire. That work he is doing or the energy he is giving is called as loss. I'll write all these things now so that you can understand this easily. In a real flow, resistance against flow is observed. Resistance against flow is observed. Now what will happen if resistance is there? Now whenever resistance is there, you will try to give away some amount and move further. You will try to give away some amount and move further. Okay, that amount you are giving, ask yourself, are you desiring to give that amount? No, you're not desiring to give that amount. For example, I'll tell you, this is a very casual example. Just take it as a joke and leave it. Okay, don't think deeper into this example. Okay, imagine you are traveling from some location A to B. You're traveling. Okay, ideally when you're traveling, let us say you're moving on a bike, ideally you're supposed to carry a helmet, you're supposed to carry all the documents required and all, and move further. But in a real case, mostly what happens, something will be missing. Let us say the policeman catches you. That is a kind of resistance against your motion now. So what do you have to do? You have to give away some amount and move forward. Is it not? I'm not talking about bribe over here. I'm just talking about some, let us say, challan, something like that. That's why I said, take it casually only. Now, what you are giving over here, what you are giving away over here, that is not desirable by you, but still you are giving it. That is why it is called as loss. Same thing over here also. Whenever a real flow takes place, you will have some type of resistance. These resistances can be by the virtue of friction in a flow. They can be by the virtue of eddies in a flow. We will study something called as eddies later on. Eddies also will create some resistances. Okay, something called as reversal of flow or eddies will create some resistances. Whenever these resistances are encountered, the fluid will say, chalo jaldi jaldi aage badho, give some amount to these people and let us move forward. That amount the fluid is giving is not desired by the fluid. It is not desired. Since it is not desired, but still he is giving, that is why it is called as loss. Okay. In a real flow, resistance against flow is observed. The fluid gives away certain amount of energy in order to overcome the resistance. This energy is called as loss. Loss per unit weight is called as head loss. Loss per unit weight is called as head loss. I'm going to represent with small h. Head loss I'm going to represent with small h. Okay. Now to understand this thing, let us say you are having some flow taking place. Imagine some flow is taking place. There is a particular pipeline. Imagine the flow is taking place in this direction. Real flow is taking place. Some section 1, some section 2 over here. Real flow is taking place. Now, first thing I can say is H1 is not equal to H2. H1 is not equal to H2. Again, put the same logic. If H1 is not equal to H2, who is greater over here? Who is greater over here? You see, as you are moving forward, you are going to give away some energy. Every time you encounter some loss, you are having some resistance against the flow. Someone is working against you. These are all resistances. You're going to give away some energy everywhere and keeping on moving forward. So basically, initially you are having higher energy. Initially you are having higher energy. Later on you are having lesser energy. In such a case, if I want to make these two things equal, if I want to make H1 and H2 equal, that means H2 I should give some, that means H2 I'm supposed to add something over here. If I add head loss over here, they are going to become equal. So basically the equation now becomes P1 by gamma plus V1 square by 2G plus Z1. And over here you are having P2 by gamma plus V2 square by 2G plus Z2. These two are initially not equal, but if I add over here head loss, then they are going to become equal. This is the Bernoulli equation in the case of real or actual flow. I hope this is clear to all of you. Since your energy is decreasing, you're supposed to add over here so that it becomes equal. This is a concept of losses. With this, we complete the limitations and assumptions in Bernoulli equation. You can take a snapshot of this particular slide. Is it all clear to all of you? Chali, let us move further now. Someone is asking me, is loss only due to viscosity? The answer is not only due to viscosity. Not only due to viscosity. You can sometimes, of course, if the fluid is viscous only, then you'll be having losses. But don't think that only viscosity is contributing. Energy head is not decided only based on height difference. Don't worry. H2, there is no problem there is no problem if this level is higher, it does not mean it should have higher energy. Don't think like that. Only its datum is higher. Probably his velocity and pressure are lesser. Probably section 2's velocity and pressure are lesser. Okay. Now let me move further to the next topic, which has already been touched by one person over here. This topic over here is regarding a concept known as kinetic energy correction factor. Kinetic energy correction factor. Correction factor. Kinetic energy correction factor. This is represented by alpha. Kinetic energy correction factor represented by alpha. Very, very commonly asked questions in IES and PSC examinations. IES and state level PSC examinations, very important. GATE examination, it is there, but generally GATE does not ask any question from here. Kinetic energy correction factor. Now, what is this basically? To understand this thing, I'll give you an example. First, I'll start with an example, then I'll come to this particular concept. Imagine I give you three numbers. Let us say the numbers are 6, 9, 12. Three numbers. I ask you to find out. I ask you to find average of squares. Average of squares. Okay. And you find, let us say you have misunderstood me and you find square of averages. Square of average. I hope this is clear to you. I ask you to find average of squares and you find square of average. Basically, you have just changed the sequence or the order of what is supposed to be done. Let us see now. If I was supposed to find out average of squares, now square of this thing is 144, square of this thing is 81, square of this thing is 36. 36, 144, 180, 180 this thing, 261. 261 divided by 3 is supposed to give you something around 87, let us say. This is supposed to be the answer over here. 87 is supposed to be the answer. Okay, this is what I wanted to know. But what did you find now? Square of average. Let us say average of these three things is going to be 9. 9 square is equal to 81. Now you see, just by changing the sequence over here, you have got a wrong answer. You have got a wrong answer. But imagine that you are having some number 8, 8, and 8, identical numbers. And if I asked you, find the average of squares. Square is 64, 64, 64. Average of 64, 64, 64 is 64. But you have found out square of averages. Average of all these three numbers is 8. Square is again going to be 64. So now what am I observing over here? I am observing over here that whenever I'm having different numbers and I'm doing a mistake over here, then my answer is getting wrong. But when I'm having same numbers, I'm doing a mistake over here, still my answer is correct. Still my answer is correct. I hope you have understood all this. This is not fluid mechanics. This is just basic mathematics only. As a matter of fact, this concept is there in your 11th, 12th class in the name of a topic called as inequalities. There was a chapter probably by the name inequalities. Over there, you might have found these kind of problems. Okay. Now, where is this related to my subject? Let us see. Okay. If you want to write this down, because I'm going to erase this thing, here only I'm going to draw a particular diagram for you to see. Where is this going to have an influence in our subject? That is where you'll understand the concept of kinetic energy correction factor. If you have taken this down, If you want to take it, otherwise it's not required. It is just for understanding's sake. Now look over here. Imagine that there's a particular flow. There's a particular flow. Some flow you're having. In this flow, let us say the velocity profile at a particular section is something like this. The velocity profile is something like this. This is the velocity profile, let us see. The velocity profile is something like this I'm having. At this particular section, if someone asks you, if someone comes up to you and asks you, what is the velocity head? The question over here is velocity head is equal to how much? Is equal to how much? Generally, we say the answer is equal to v square by 2g. What is v over here representing? V over here is average velocity of flow at the section. Average velocity of flow at the section. So basically, what have you done? You have taken average and then you have squared average. You have taken average and then you have squared average. So this is what you have done. But really, if you think logically, what were you supposed to do? You were supposed to take this velocity head. You were supposed to take this velocity head. Likewise, take each of the velocity heads and then you are supposed to find out the average. So basically, you're supposed to take v1 square by 2g plus v2 square by 2g. Likewise, you are supposed to take their weighted average. So basically, you are supposed to have squares and then you should have taken their averages. I hope you are following. This is what we were supposed to do at this section, but we have done this thing. So now what happens? Whenever my velocity profile is non-uniform, that is when I'm going to have an error over here. This entire thing will become wrong. But what if my velocity profile is uniform? If my velocity profile is uniform, it is like 8, 8, 8, 8 everywhere. That means even if I do this particular mistake, answer is going to remain same. That is when there is going to be no mistake in v square by 2g. I hope you are following what is happening over here. This is a very, very logical thing. The logic is whenever we are having a non-uniform velocity profile, that time when we take the velocity head, it corresponds to average velocity of the flow. And when it corresponds to average velocity of the flow, we have done a mistake over there. We were actually supposed to find out average of all the velocity heads. We were supposed to find out average of all the velocity heads. But what have we done? We have taken the velocity head of average velocity. यहाँ पे mistake हो गया. So what is going to happen? This value is 81, whereas it was supposed to be 87. Example sake, it is 81, whereas it was supposed to be 87. So now this value is lesser than the actual velocity head. So actual velocity head is actually supposed to be equal to some factor multiplied to v square by 2g. This some factor we are having, alpha we are having, that is known as your kinetic energy correction factor. And remember, your kinetic energy correction factor should always be greater than or equal to 1. क्योंकि जो आप पता कर रहे, what you are estimating is less than the actual value. It is less. Therefore, you should have something greater than 1 multiplied so that 81 becomes equal to 87. When equality holds good only in one particular case. Which particular case is that? When you are having uniform velocity profile. I hope the idea is now clear. Then I can write down some notes. I hope the idea is clear to all of you till here. Fine. We are not assuming ideal fluid from here on. Once we have defined Bernoulli equation real flow, from here on we are going to apply Bernoulli equation real flow only. So don't think that the fluid is any more ideal. Now we are talking about Bernoulli equation for real flow, real fluid cases. Okay. We are now speaking about Bernoulli equation real flow only. That is why you can have a non-uniform velocity profile. So let me write some notes over here regarding alpha along with the formula, along with some standard values of alpha you are supposed to remember. Okay? The notes go something like this. Look over here. The velocity hit in a non-uniform velocity profile, deals with average velocity of flow, average velocity of flow. This underestimates the actual velocity hit. What is the meaning of underestimate? Underestimate means you are finding something lower than the actual value. You are underestimating. Okay. This underestimates the actual velocity hit. Since it is underestimating the actual velocity hit, therefore actual velocity hit is supposed to be equal to how much? It is supposed to be equal to your found out velocity hit multiplied to. Now, since you have underestimated something and you are supposed to now properly estimate it, you are supposed to raise its value. Therefore, you are supposed to multiply with something greater than 1. This is your kinetic energy correction factor. What is the formula for alpha? Alpha is equal to 1 by AV cube integral of U cube times dA. The integral is supposed to be done over the entire area. What is the meaning of these things? Capital A over here is cross section of flow. Capital V over here is average velocity of flow. Small u over here, look over here. All these are small u's only. All these are small u's. Small u over here is local velocity of flow. And dA over here stands for cross section corresponding to local velocity. Cross section corresponding to local velocity. Okay, this is the value. Moving further, the value of alpha is supposed to be always greater than or equal to 1. Okay, equality will hold good only in uniform velocity profile. Alpha equal to 1 in the case of uniform velocity profile. Alpha will be 1 only in the case of uniform velocity profile. Otherwise, it is supposed to be greater only. As a matter of fact, alpha in the case of laminar flow through pipes, laminar flow through pipes is going to be equal to 2. This is the value you are going to have. Furthermore, alpha in laminar flow, remember this thing, is always supposed to be turbulent flow. Alpha in laminar flow is always supposed to be greater than alpha in the case of turbulent flow. Okay, these are the notes regarding your concept of kinetic energy correction factor. In the next chapter, you are going to have one more correction factor similar, known as momentum flux correction factor, represented by beta. Only difference over there is, instead of cube, you will be having square and a square over here. Concept will be same. Instead of cube, you will be having square. That is beta, called as momentum flux correction factor. It will be called as momentum flux correction factor. So this is the concept of kinetic energy correction factor. You can take a snapshot very quickly. We'll move further. This is very, very important result. This is a very important result. Regarding these differences with the open channel flow, you will have to incur with the open channel flow faculty. I don't teach open channel flow. I do not know that also. So better you speak to open channel flow faculty for that. This is deals. Chaliye. Please remember this value. For laminar flow through pipes, the value is equal to 2. Exactly 2 value will come. Okay, that is a standard question. Derivation is a standard question in IS conventionals. Okay, you are supposed to, in IS conventionals, these kind of questions come. Derive the value of alpha for laminar flow through pipes. Let us now move further. After having discussed the concept of alpha, okay, very good question. Why is the value of alpha greater in laminar, lesser in turbulent? I'll discuss that when I'll discuss laminar and turbulent better. Otherwise, if you can understand, remember this thing. Alpha is going to be higher whenever the variation of velocity is higher. Whenever variation of velocity is higher. In laminar flow through pipes, you are going to have parabolic velocity profile. Variation is very strong. In turbulent flow, the variation is not that much strong. You are going to have logarithmic velocity profile, which looks almost like a rectangle. This is your turbulent flow, and laminar flow will be something like this. Now, stronger variation in laminar flow, therefore alpha higher over here and alpha over here lesser. This is the reason why laminar flow is going to have higher value. Don't worry, these things you'll understand once we go into that topic. Right now, just remember. Now, what I'm going to discuss over here is very, very important concept. Please concentrate. Do not mention anything for some time. I guarantee you, if you listen properly, you'll understand things. Okay. Whenever we are going to deal with Bernoulli equation concept, finding piezometric head difference becomes important. Piezometric head difference means delta H star, which is equal to, let us say, H1 star minus H2 star becomes very important. Imagine a passage over here, you're having. In this passage, this is some point 1, this is some point 2. I want piezometric head difference. If I want piezometric head difference and I ask you, you might suggest to me, okay, sir, do one thing. You install piezometers over here. After installing piezometers over here, you will see that the fluid is rising up to some level over here, Whatever is the difference between these two levels, the difference is equal to delta H star. You will suggest this thing. It is perfectly correct also. Nothing wrong with this. But practically, there is something wrong over here. What is practical problems? The first practical problem is when you are having a gas flowing over here, imagine a gas flowing over here, you cannot use this thing. Why? Because gas will never form an interface. One problem we have. Second problem, imagine liquid instead of gas, imagine liquid only. ठीक है, liquid. But liquid is moving with a very, very high pressure. Imagine extremely high pressure liquid is moving. So now what happens? The height of this particular tube has to be extremely tall, which is not practical in many cases. See, you have some limitations. You have to work within those limitations. So that height cannot be much tall also. That is why you have to think of some other plan, how to find out the value of delta H star. And let me tell you, this delta H star is very, very important. You will be seeing the importance of delta H star in the next devices that you're going to use, like venturimeter, orifice meter and all. Over there, delta H star becomes important. So our idea is now very good. Our idea, someone has suggested, our idea is basically instead of doing all these things, recall in manometry also, when these things came into existence, we started using manometers. So now what we are going to do over here is, I'm now going to use a manometer over here. I'm now going to use a manometer over here. So imagine, look over here. Imagine you're having some passage, something like this. One moment, please. Suppose this is some passage you are having. Sure. This is some passage you are having. You are having some flow taking place over here. There is some flow taking place over here. There is a working fluid over here. Okay. And you have installed a manometer. Suppose you install a manometer. Let us say you install some manometer over here. The manometric fluid, let us say, is taking some position. The manometric fluid has chosen some position over here. This is a position attained by the manometric fluid. Okay. I'm having a certain point over here. Let us say the point is 0.1. I'm having some point over here. This point is 0.2. I'm choosing a reference datum. The reference datum, you know, is up to us. That is why I'm deciding this as my reference datum. Let us say this is Z is equal to 0, reference datum. And I'm measuring some heights now. The heights I'm measuring is from here till here. So this height first of all, and then this height. These two heights I'm measuring. This first height over here, this first height over here is Z1. The second height over here is Z2 height. Furthermore, let us say I have measured this height also. This height, let us say, is equal to some height HM. this height is equal to some height hm. Okay, so basically I want to get the value of delta H star in terms of hm. Terms of hm, you have to memorize the formula we are going to get from here. Concept is very simple. Concept is very simple. You know already how to deal with these kind of problems. Let us say you take this point as point x, you take this point as point y. You are going to say straight away that the value of pressure at point x has to be equal to the pressure at point y. This is what we are going to start with. Then we will say, ठीक है, pressure at point x and point y, both of them are same. Sound is very low. Is the sound clear now? Is the voice clear now? Is the voice clear now? Okay, fine. Okay, if you can hear me scrolling, then that is very good. Chaliye. Pressure at point X and point Y, both of them are equal. HM over here is basically the difference in the manometric fluids level. That is HM over here. Okay. If I want to find out the value of delta H star in terms of HM, I'm starting with these 2 points. The pressure at point X is equal to how much? Let me start from here. The point 1 is having some pressure P1. I'm coming down, therefore plus. I'm having the fluid over here, gamma working. Therefore, gamma working times Z1. So I have reached till this particular point. Okay, now pressure at Y. I'm going to start with P2 over here. The pressure at this particular point is P2. I am coming down only up till here. So therefore, plus gamma working multiplied to how much? Z2 minus HM. Z2 minus HM. Next, I'm again coming down from here till here. So again, plus gamma manometric into how much? Gamma manometric into how much do I have over here? Plus multiplied to HM. Gamma manometric multiplied to HM. This is a value. Now I can say both of them are equal. Both of them are equal. Now look at this. P1 over here is static pressure. Gamma W into Z1 over here is hydrostatic pressure. Sum of these two is what pressure? Piezometric pressure. Let me take piezometric pressures on one side. So I have over here P1 plus gamma W into Z1 minus P2 plus gamma W into Z2. Look over here, P2 gamma W Z2 I have taken on the left hand side. This has to be equal to how much? It has to be equal to gamma M into HM minus gamma W into HM. This is the value I'm having. This is the value I'm having. Okay. Now this pressure over here is P1 star minus this pressure over here is P2 star. So P1 star minus P2 star is basically delta P star is equal to how much? Delta P star is equal to HM multiplied to gamma M minus gamma W. Gamma M minus gamma W. Okay, fine. Now I can say delta P star is this much. If I want delta H star, so I can say delta H star is supposed to be delta P star divided by gamma of working fluid. Because we know head is equal to pressure divided by gamma. So if I divide this by gamma of working fluid, then the value of delta H star now becomes equal to how much? It becomes equal to HM multiplied to gamma M by gamma W is SM by SW minus gamma W by gamma W over here is supposed to be 1. This is the formula we are having. This is a formula you're supposed to memorize. Delta H star over here is HM into SM by SW minus 1. Memorize the formula. Memorize the formula. Okay. So we have got the value of difference in piezometric head in terms of manometric head over here. Furthermore, sometimes what happens? Sometimes what happens? If SM is much greater than SW, What do I mean by this? The manometric fluid over here, this is manometric fluid over here, gamma m or sm is a property. It is much greater than SW. Much greater than SW means what? Imagine this over here is a liquid and this over here is a gas. So his density will be much greater than the density of working fluid, of course. In that case, what happens? If this happens, it implies that Sm by Sw becomes much greater than 1. Much greater than 1. If this condition arises, then Sm by Sw becomes much greater than 1. This implies in this particular case, the value of delta H star is approximated, very healthily approximated. That means it's a very good approximation. It is approximated as how much? Hm multiplied to Sm by Sw. No need of -1 now. Because you see, Sm by Sw is much greater than 1. Let us say this is 800 and this is 1. So if you're having 800 minus 1 or just 800, both of them are almost same only for us. That is why we will just say this much is the value. So be careful, whenever this happens, you can use this particular condition over here. This is approximation we are having. Fine. Now this approximation is important because in GATE examination, they are using this approximation. Okay, some years back in civil paper, this approximation was used in the solution. Only then you were getting the answer. Otherwise, you would not get the answer. Okay, you can take a snapshot of this particular slide. If anyone wanted this particular slide, you can take down quickly. Where is it applicable? I'll mention to you those things. Where it is applicable, I'll mention to you these things. Now for homework, I'm going to give you one homework over here. If you're having an inverted YouTube manometer, you have to get the value of delta H star. So let me write a homework over here. Homework over here is something like this. You're having this particular case. You're having an inverted YouTube manometer. You're having an inverted YouTube manometer, let us say. Fine. And let us say you're having some fluid's presence from here to here. This is the fluid's presence you're having. And this distance over here is HM distance. HM distance. Okay. This is some 0.1. This is some 0.2. Your aim again is to find out the value of delta H star in terms of HM. You're supposed to find this particular thing out. This is the homework, inverted YouTube manometer. Okay? You can say the properties over here are gamma working or S working. The properties over here are gamma manometric and S manometric over here. You will find this thing out. You can take this slide as a homework slide. Take a snapshot of this particular slide. HM is termed as over here manometric head. HM over here is manometric fluid head. It will be useful. You won't understand it right now. You'll understand it later on whenever we are discussing the concept of venturi meters and all. That time you'll come across this concept. Previous slide is over here. You can take the previous slide. This particular equation is basic idea of head only. The value of head is supposed to be equal to pressure divided by gamma. Whenever we want to find out head, we want to find in terms of working fluid. Therefore, we are writing gamma working over here. Chali, let us move further now. This is a slide which I have done. This is a slide for homework. And now coming to the next slide over here. This is a last concept. The next slide is going to be the last concept in the first part of Bernoulli equation. If you remember, basics of Bernoulli equation was the first part. This slide is the last concept over here. This is regarding the concept of power. We are now discussing the concept known as power. The concept of power. Okay. Now, whenever we talk about fluid having some energy, then the fluid is going to have some power also, because energy per unit time is power. The reason why we are discussing power is the fluid is continuously flowing. So you're not having some mass or weight, you are having weight per unit time. Therefore, energy per unit time will come into picture, which is known as power over here. How to calculate the value of power? Very simple formula. Very, very simple formula. As a matter of fact, this formula will be used in hydraulic machinery also. The formula for power, let us see how do we get this thing. We know that power has to be equal to energy per unit time. Energy per unit time. And energy over here is equal to, or energy per unit weight is equal to head. Energy per weight is equal to head, which implies energy is equal to weight multiplied to head, which implies energy is equal to weight means m times g multiplied to head. Now in place of energy, let us say I'm writing m times g into head. So I have over here power is therefore equal to m times g times head whole divided by time. Whole divided by time. Now look at this thing, mass per time. What is mass per time going to represent? It is going to represent mass flux. Therefore, power has to be equal to mass flux multiplied to G multiplied to head. Mass flux multiplied to G multiplied to head. So therefore, from here I can say power is equal to mass flux over here is rho into Q. So rho Q into GH you can say, or you can say power is equal to gamma into Q times H. Both of them are same things. This is the formula for power. This is the formula for power. Now the question comes over here, which power is it representing? Okay, density, I understand, discharge is Q, G is G, but which power is it? Answer is very simple. The type of power corresponds to the type of head considered. The type of power corresponds to the type of head considered. So whatever type of head you take, that type of power you are going to get. For example, if I ask you what is the power loss in a particular flow, then what are you going to write? You're going to write power loss is equal to gamma into Q into which head? Head loss. Okay. If you want a particular power, you will write that particular head. If I ask you what is the power given to the turbine, what is the power given to the turbine? So you'll say power given to turbine is equal to gamma into Q into HT, head of turbine. If I ask you what is the power derived from the pump, what is the power gained from the pump, you will say power gained from the pump is equal to gamma into Q into HP. Likewise, we are supposed to deal with this thing. I hope this is clear to all of you. I hope it is clear to all of you till here. You can take down this particular formula, highlight this thing. With this, we complete the first part of Bernoulli equation. Now I'm going to start some numericals. I will take some numericals. Mass per unit time is mass flux. That is why m dot over here. Power is energy per time. Energy, I got this much. Divide by time. So mass by time is mass flux over here. Alpha formula is very, very important for IES. Extremely important for IES, the formula for alpha. Someone wanted the homework slide. Please be quick. I'll start one question now. I think I have sent some short notes for kinematics in the homework slide, solution to homework slide. Rest, whatever are missing, you can do it yourself. Very little is missing, I believe. Chali, now let us look at some questions. Look at this question over here. Imagine you are having a container. Imagine you have certain container. Certain container. This question is worth 2 marks actually in examination. Okay. But I'll go very slow only so that everyone understands. Let us say there are 2 fluids kept in over here. There are 2 fluids kept in over here. One fluid over here. And let us say, once again, one more fluid over here. These are 2 fluids kept in over here. Okay. The interface is exposed to atmosphere. The interface is atmospheric. Suppose this point is certain point A. This point is certain point B. This point is some point C. Okay. Only one question you try. This one question you try. It is sufficient for today. This will be having multiple things in it. Let us say gamma of upper fluid, gamma 1 is equal to 8 kilonewton per meter cube. And gamma of lower fluid, let us say gamma 2 is equal to 12 kilonewton per meter cube. 12 kilonewton per meter cube. Let us say the distance from here to here, this distance is equal to 3 meters. And let us say this distance over here is equal to some 8 meters. This distance B to C is some 8 meters over here. Suppose some point over here, some point over here I'm creating an orifice. There is some point where I'm creating an orifice. 1 second. At some point I'm creating an orifice over here. Orifice basically means a very small hole. A very small hole I'm creating. So now what is happening due to this orifice? First of all, let us extend this particular line. Due to this orifice, the fluid is coming out. The fluid will now emerge outside. The fluid is now going to emerge outside. The fluid, let us say, is emerging outside. I hope you're able to visualize what is happening over here. The fluid is emerging outside. Suppose we call this particular point a certain point D, certain point D. The question says, if the value of G is taken as 10 meters per second square, what is this distance over here equal to? Let us call it as R. R is equal to how many meters? This is the question asked. I hope the question is clear to all of you. You can take it down quickly. Be very quick. Jaldi draw karo. The question might look difficult. Don't worry. Don't worry if it is difficult. It is actually a 2-mark question. but we will go very slow. We'll try to understand how to approach questions over here. The meaning of triangular interface. Yes, height of D is given. I'm sorry, I did not mention height of D. I'm really sorry. Height of D is given, the distance is given. This distance, very good, 3 meters. Okay, someone is asking me what is this triangle over here? Actually, it is not supposed to be, it is supposed to be something like this. This basically means this level over here is exposed to atmosphere. But वो जल्दी जल्दी में it happens like this. Exposed to atmosphere है वो. ठीक है? चलिए, let us start now. Let us start. How to start this thing? This question, now you see the psychology of examination. I'm telling you, I stress on this thing a lot. You have to catch the nerve of examination. What is the psychology of examination? You have to understand. He says 2 marks over here. What makes a question 2 mark? According to me, the question becomes a 2 mark question either if it is having slightly higher mathematics or it is having a combination of 2 subjects. This question does not have higher mathematics, very simple mathematics, no need of calculator also. But this question is having 2 combination subjects. What are the 2 combination subjects? This question is fluid mechanics plus engineering mechanics question. This question over here is fluid mechanics plus engineering mechanics question. Now, where is fluid mechanics? Think logically now. This fluid and this fluid over here is going to create certain pressure at this particular point. Then what is happening? The fluid coming out. Just imagine the fluid was having some pressure. The moment fluid comes out, imagine before D you're having some point over here, after D you're having some point over here. 1 second. If I spoil this diagram, it will be difficult for you. So I'll leave this slide as it is. I'll make a duplicate slide over here. Okay, this slide is 14F. It will remain as it is. In 15F, I'm doing solution. Now look over here. Some point over here, D prime is there. Some point over here, D double prime is there. What can you say regarding D prime? D prime is going to have a very high pressure. Pressure is extremely high. And what about velocity over there? 0. Remember one rule. Whenever you talk about tanks or reservoirs, inside the tank or reservoir, every point we are going to assume is having 0 velocity. Because the cross-section area over there is as good as infinite, therefore the velocity is 0. Now what is happening? The fluid is moving from D prime to D double prime. At D double prime, what will happen? Its pressure is becoming 0. Why is its pressure becoming 0 over here? Because it has come out into atmosphere. It has come out into atmosphere. Therefore, the pressure over here is 0. Now you see what is happening. Pressure energy is decreasing. Always think of this concept. P plus K plus U equal to constant. Ideal condition, nothing regarding loss is given to me. So P plus K plus U equal to constant. Now tell me, the moment he is going from D prime to D double prime, his pressure is going down. So who is increasing now? His kinetic energy is increasing. So now he is going to develop some velocity. He will have certain amount of velocity over here. Till finding the value of velocity, my job is fluid mechanics. After you got the value of velocity, to find the value of R, that part is engineering mechanics. Both these things combined, the question is for 2 marks. In fluid mechanics also, you're having 2 parts. The first part is statics part. The first part is over here, statics part. You know that this is interface, you know the gamma value, you can find the value of D prime's pressure. Finding D prime's pressure, finding pressure at D prime, it's statics part. Then finding the value of velocity is Bernoulli equation part. Finding the value of velocity is equal to how much? That is Bernoulli equations part. I hope you are able to break down the question now. Okay, this much breakdown you don't have to do in examination. Straight away you can start. I'm showing you, probably you're seeing some questions the first time. Therefore, I'm showing you how to break down a question. Chaliye. So my concept is quite clear now. There are 3 steps involved. First step is to find the pressure at D prime. Second, that is statics part. Second step is to find the velocity outside. That is Bernoulli equation part. After finding the velocity, then I have to use some common sense from engine mechanics. I have to find the value of this R. I hope this question is clear to all of you now. Chaliye. Let us start now. Chaliye, let us start now. I'm going to start first of all with pressure at D prime is equal to how much? The question now is solution over here. Pressure at D prime is equal to how much over here? It is supposed to be equal to gamma 1 multiplied to 3 plus gamma 2 also multiplied to 3. So it is equal to gamma 1 multiplied to 3 plus gamma 2 multiplied to 3. I hope you are getting this thing. This height is 3 and this height also, BD also is equal to how much? 3 only. So gamma 1 multiplied to 3 with gamma 2 multiplied to 3. If you check this thing, no need of calculator. Please avoid calculator for this question. I have given very simple cases. G also have given us 10 only. Okay. So this is going to be 8 into 3 is 24 plus 12 into 3 is equal to 36. This implies PD prime. PD prime is equal to how much? 60 kilopascal. This is the value of PD prime you are going to have. Next, from here to here, I can apply Bernoulli equation. I can apply Bernoulli equation between these 2 points. Between these 2 points, I can apply. So first topic is done now. Applying Bernoulli equation. By Bernoulli equation. By Bernoulli equation. What do you have now? You have over here PD prime divided by gamma plus which gamma? The fluid is having which gamma over here? Gamma 2 only. Plus VD prime square. VD prime square divided by 2G plus ZD prime has to be equal to, outside you are having a point, let us say PD double prime by gamma plus VD double prime square divided by 2G plus ZD double prime. Now you see what is happening. Straight away I can cancel these 2 things because both of them are same. Both of them are same. Inside the reservoir, velocity is equal to 0. Velocity is equal to 0 inside the reservoir. Outside the reservoir, the pressure is equal to 0. Pressure is equal to atmospheric outside the reservoir. Therefore, 0 over here. Gauge pressure is 0 over here. So now I can write the value of velocity is equal to how much? Velocity is equal to root over of 2G multiplied to PD prime divided by gamma 2. Gamma 2. Let us look at this answer. This should not be very difficult for you. This will be equal to root over of 2 times 10 times pressure is equal to 60. I am taking pressure in kilopascal, therefore I'll take gamma also in kilonewton per meter cube. That is equal to 12. 60 by 12. Orally you can answer. 60 by 12 is 5. 5 into 2 is 10. 10 into 10 is 100. Root over of 100 is equal to 10. Velocity is equal to 10 meters per second. This is also done now. This is also done. So basically fluid mechanics part is done. Now what I'm going to do is purely engineering mechanics. Okay. Chali, quickly see this is all clear to you or not. Pushpendra Dawar, perfectly correct answer. Chali, now let us look at how do you find the value of R. People are saying that it is projectile motion. Correct. It is projectile motion, but it is half of projectile motion. Okay. Half of projectile motion. So I'll go by basic law. Without projectile only I'll go. 1 second. I have duplicated the slide now. 1 second. Now you have to be careful over here. You have to be careful over here. If you are going by projectile motion, please understand it is basically R by 2. R over here is range formula by 2. R is over here range formula by 2. And this V over here is representing what? It is representing initial velocity V into sine theta. Sorry, cos theta. V into cos theta it is representing. But I will go by basic mechanics only over here. My logic is simple. Look at this carefully. This is what I'm discussing over here, mechanics. The logic over here is when the particle is moving from here to here, it is traveling some distance in y, it is traveling some distance in x. The distance in y it is traveling is basically d to c, that is equal to 5 meters. It is traveling some distance in x, that is equal to r. Whatever time it is taking to travel in y, same distance, same time it is taking to travel in x. So I will write over here. I'll start with displacement in y. Displacement in y is equal to uy into t plus half of ay into t square. Now look over here. Velocity is completely in x. Therefore, this value is 0. Initial velocity in y is 0 over here. If I take the displacement in y over here as 5 units, I'm taking downward direction positive, then half of g over, sorry, ay over here is g basically 10 units multiplied to t square. Multiplied to t square. From here, I get the value of t is equal to how much? 1 second. The value of t is equal to 1 second. This is what I have. Okay, I have found out the displacement in y. Next, taking the same time, I will talk about displacement in x. It is equal to uxt plus half of ax into t square. Remember, whenever you have projectile motion, the value of acceleration in x has to be equal to 0. Acceleration in x is equal to 0. So now you can see this value over here is r. R is equal to how much? Ux is basically this velocity v, that is equal to 10 multiplied to time is equal to 1. Therefore, the value of r is equal to 10 meters. Remember, whenever you deal with these kind of projectile motion problems, always remember the connecting link between vertical motion and horizontal motion is the time. Both important here. Connecting link, whatever is the time taken in these equations, that is y equations, same time is taken in x equations. Accordingly, you can manage of things. So the answer over here is 10 marks. Sorry, 10 meters over here. 10 meters is the answer over here. Okay. With this we complete. Now you can raise hand. I'll talk to you if you have doubts. Shankar.
Sir, I have a doubt in kinetic energy factor, sir.
Kinetic energy correction factor.
Yes, sir. Like we are considering here the average velocity. That is why we are multiplying that factor, sir.
We are considering average velocity. Since average velocity is considered, it is going to have an error. That is why we are looking at kinetic energy correction factor.
Okay, sir. And
Bernoulli equation. Look at Bernoulli equation. What is this V1 over here? Average velocity at section 1. If it is a pipe, then it is average velocity at section 1. Similarly, V2 is average velocity at section 2. That is why we have to consider alpha over there. Okay, no?
okay, sir. And I have a doubt in previous ESC questions, sir.
Tell me.
There is a statement, sir. The rotation of fluid is always associated with shear stress.
Okay. This statement actually is wrong, but they have said it is correct statement, right?
Yes, sir. Yes, sir.
This statement, strictly speaking, is wrong. If you go by actual physics, that statement actually is wrong. Okay. But they have mentioned it is a correct statement. I'll tell you why it is wrong. There is a possibility of shear without rotation. Shear without rotation is possible. Similarly, rotation without shear is also possible. rotation without shear is possible. What do I mean by this thing? Look at the first case. Imagine you are having a fluid element like this. The fluid element is shearing to form something like this. Hello, are you able to listen?
Yes, yes, sir.
But imagine the center of gravity was over here. Again, the center of gravity is over here. If the center of gravity was initially over here, initially over here, later the center of gravity went over here in a straight line, then you are having shear over here, but no rotation. How can I say shear is there? Because you see, angle has
Angle
changed.
deformation. Yes,
Yes,
sir.
but there is no rotation possible. So when is shear without rotation going to take place? When both of them are moving in the opposite direction with the same angular velocity. The same angle.
Yes.
That is
Yes,
when
sir.
you are having shear without rotation. Then what about this particular case? Imagine you are having a fluid element like this. Fluid element like this. Its center is somewhere over here. Now the fluid element, this length, look at this length, is tilting over here like this. Look at this length, it is tilting over here like this. Both of them are tilting by same angle. That means previously also 90 degrees was there, now also it is 90 degrees only.
No shear.
Rotation has taken place. So shear is not there.
Yes, sir.
Rotation has taken place.
Yes,
So
sir.
strictly speaking, rotation need not be always associated with rotation can be without shear also possible. Okay, but that is
Okay.
only one case. But still ESC has taken that statement as correct statement. So for ESC examination, you consider that statement to be correct. Apart from ESC examination, the statement is wrong.
Okay, sir.
Okay.
Sir, and can you solve just in the class like tomorrow, sir?
Can I solve
There
what?
there is a gate question, sir. Gate 20 question.
Hmm.
Like they have given a graph, sir.
Hmm.
Uniform flow with velocity u makes an angle theta with y-axis, and they have given some graphs, sir. I'm not getting that question.
Uniform flow with
Velocity u make an angle theta with y-axis as shown in the figure. The velocity function potential is, they have given the question like this.
velocity potential is how much? The
Yes, sir.
equation velocity potential function is equal to how much?
Yes, sir.
Making angle theta with which axis?
Y-axis, sir.
Y-axis. Okay, fine. The velocity. So the value of v is equal to how much over here? V is equal to, that is the y component of velocity is equal to how much? U cos theta.
Cos theta.
The value of small u is equal to how much? Capital U sin theta.
Okay.
Capital U sin theta. Now you can find out the function phi.
Okay, sir.
Because you know this is equal to minus of dou phi by dou y, and this is equal to minus of dou phi by dou x. From there you get the answer, right?
Okay, sir. Okay.
Cheers.
Thank you, sir.
Shivani. Shivani,
Hello.
hello.
Yes,
Can you be
sir.
louder, please?
Yes, sir.
Not again.
So you have derived equation for delta H star in terms of HCM, right, sir?
Delta H star.
So what is the delta H star, sir? What is its significance?
Delta, that significance will come later on actually. Delta H star basically represents the difference in piezometric head at this point and this point. These 2 points are going to have different piezometric head. Many people have asked this question. Let me clear it now. Why delta H star is important? Delta H star is important for finding velocity. Why? You see over here, P1 by gamma plus V1 square by 2G plus Z1 is there. P2 by gamma plus V2 square by Z2 is there. Now P1 gamma plus Z1 combined is going to be equal to delta H star. So delta H star, sorry, not delta H star, it is H1 star. Not delta H, 1 second please. It is not delta H star, it is H1 star. P1 by gamma plus Z1 is H1 star. So I'm having H1 star plus V1 square by 2G. P2 by gamma and Z2, both of them combined will give you what? H2 star. So you're having H2 star plus V2 square by gamma. Now what is delta H star? Delta H star is H1 star minus H2 star. H1 star minus H2 star is equal to delta H star. And delta star is basically representing what? It is basically representing delta V square by 2G. Because if you take that H1 star and H2 star on one side, you are left with what? V2 square multiplied by 2G. Are you following this thing?
Yes, sir.
So the purpose of delta H star will always be to identify the velocity. Somehow you will get some relationship velocity from there. Is it clear?
Okay, sir.
That is
Thank
why
you.
delta H star is important. Later on in Bernoulli, in Vinci meter and all those things, we will use the delta H star directly. Okay?
Okay, sir.
Okay, thank you. Vishnu J. Nair.
Good morning, sir.
Morning, sir. Tell me.
Sir, my doubt is, sir, how we will get this P1 by gamma, sir, that pressure head?
P1 by gamma. We get P1 by gamma. I'm not. Your question is highly vast question. Can you be specific? Means regarding.
Sir, I didn't get how the pressure head will become P1 by gamma. That's all.
Acha, why is pressure head represented as P by gamma? Is that a
Yeah.
question?
Yes, sir.
Okay. Okay. Let me answer you in a way which hopefully will be easy to understand. Imagine that there's a particular flow over here. There's a particular flow over here. Imagine, sir, there is a particular section. This is some section I'm having. In front, I'm having one more section. Let us say this is one more section I'm having. Okay. Now this blue section is pushing. The blue section is pushing the other section over here. He is pushing the other section. Now, whatever he is pushing with, that is called as what?
Static head.
Pushing is basically equal to what? Static pressure. So basically he's saying you keep moving now, I also want to move. He's basically trying to drive the motion, drive the flow. That is called as your static pressure. Till here everything is clear?
Yes, sir.
Okay, fine. Now what I do is, I expose over here to atmosphere. I expose over here to atmosphere. Remember one thing, the moment you expose anything to atmosphere, the moment anything is exposed to atmosphere, immediately what happens? The pressure becomes zero. Are you following this thing? I gave you an example a few days back. Imagine you are having a bottle with a cap over here, with a cap over here. You are pressurizing. When you pressurize, when you press the bottle, that time basically static pressure is available. Pushing pressure, P is available. But the moment you slightly open the cap, what happens? It is exposed to atmosphere. The pressure is now becoming what?
Zero.
Zero. The moment pressure becomes zero, now you see P plus K plus U equal to constant is there. The moment pressure is becoming equal to zero, pressure is decreasing, let us say, pressure is becoming zero, kinetic energy is not rising over here. If kinetic energy is rising, basically discharge is increasing, you should say. That is not happening over here. But what is happening over here? Potential energy of these fluid particles is rising up. The fluid is going to rise up. In which device? What is this device over here? This device is called as, remember, a device which does not block the flow but exposed to atmosphere. That is called as what?
Piezometer.
If it blocks the flow and exposes to atmosphere?
Pitot tube.
Pitot tube. Perfect, sir. So now he is, this is happening now. So who has increased over here? Datum has increased over here. Now after datum increases over here, now what happens? This much height, let us say at this particular point, this much height is developed. What is this height over here? This is the height of fluid required to maintain this much of pressure. It is a height of fluid required to maintain this much of pressure. This height of fluid is called as pressure head. It is called as pressure head. It is a height of fluid required to maintain the pressure at this particular point. Are you following this thing? This point's pressure was becoming zero, so he went up. Now you are having some pressure throughout over here. This pressure head has to be equal to how much? This pressure head has to be equal to whatever is the pressure over here, that is P divided by gamma. It is P divided by gamma. Are you following now the meaning of P by gamma over here? How do we get this? If you, let us say you're having a doubt, how do we get this pressure head? Suppose between this point, let us say point 1 and point 2, I'm applying Bernoulli equation. Between point 1 and point 2, I'm applying Bernoulli equation. So P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2. Okay, so fine.
Okay, sir.
Now you see the velocities, both of them are equal to 0. Let us say there is no motion taking place. Velocities are equal to, let us say, the value of Z2, I'm taking is equal to 0. The value of Z2 I'm taking is equal to 0. The value of P1 is equal to 0. Why is P1 equal to 0 over here? Exposed to atmosphere.
Sir.
Z1 is equal to this particular height. That height is basically equal to P2 by gamma or P by gamma over here. Are you following? So this height is basically supposed to be equal to what? P by gamma. So what is P by gamma representing? If you have a doubt, then P by gamma is basically representing the height of the fluid column required to create the pressure at this particular point.
Okay, sir.
Is it clear now?
Got it, sir. Got it, sir. Sir, and one more doubt, sir.
Sure.
The last problem you discussed now. Sir, I didn't understand how we get Sx equal to 10 meters, sir. Ut into half ft square.
See, do you understand? Did you first of all understand this equation? Look at my cursor. This equation is fine.
Okay, sir.
See, whenever you deal, remember one thing, something in physics you have to remember, that is, whenever you're having this kind of motion, which is called as curvilinear motion. In curvilinear motion, you're going to have x-axis motion separate and y-axis motion separate. Hello, are you able to listen?
Yes, sir. Yes, sir.
X-axis motion separate, y-axis motion separate. But both these motions are interconnected with what parameter? Time parameter.
Time.
Okay, they're interconnected with time parameters. So what I'm doing over here, I'm using y-axis motion. I'm finding how much time the particle is taking from here to move down. Okay, I'm taking how much time the particle is taking to move down from here to here in y-axis. So y-axis displacement is equal to 5, acceleration is 10. From there I get the value of time t equal to 1 second.
Okay, sir.
There is some disturbance behind. Please ask them to keep quiet. Okay. Somehow I got the value of time is equal to 1 second. After getting the value of time equal to 1 second, I'm using the same time for finding how much displacement is in x-axis. For that, I'm writing this equation. Okay, you have the equation S is equal to ut plus half at square.
Yes, sir.
That only I'm writing. But in this case, the acceleration in x has to be equal to 0. Remember this thing. X-axis acceleration has to be equal to 0.
Sir, I didn't get that how half at square becomes 0, sir.
How?
Half at square acceleration becomes 0.
Acceleration on Earth in x-axis is equal to 0. When you throw something,
Oh, okay, sir.
only acceleration is in vertically downward. Okay?
Okay, sir. Got it.
Okay, thank you.
And sir, one more, that how we get the u is equal to which u should we take, sir? Is that v double prime or?
Velocity over here, because now you are into mechanics part. This part, once velocity is developed, so that velocity you are supposed to take over here.
Okay, sir. Got it, sir. Thank you, sir.
Okay. Thank you.
Good morning,
Harish,
sir. Yeah,
morning, ma'am.
yeah, yes, sir. I have a doubt in that previous question one.
Okay, tell me.
So for a two-dimensional irrotational flow, with the velocity potential is defined as phi is equal to log e bracket x square plus y square. Which of the following is a possible stream function psi?
In this question, there were two options correct actually. If you check this thing,
Yeah.
two options were correct. That was an ambiguous question, but don't worry, that will not happen. Prefer from here onwards, prefer u is equal to minus dou phi by dou x, and v is equal to minus of dou phi by dou y. Okay. Now those in that particular year, those who gave any of those two options correct, both of them got the correct answer. Both of them got marks for that because both the answers are correct then. Okay.
Okay, sir.
Okay, so you can see the solution. It is basic differentiation solution only. You can see the solution. Two answers are correct. Both of them are correct. Both of them got the correct complete marks over there. Don't worry.
Okay. Okay. Thank
That
you.
is a doubt, right? Both
Yeah,
are
yeah, yeah.
fine. Okay.
Thank you.
Thank you.